On April 13, 2029, a date that is already circled on the calendars of astronomers and planetary defense experts worldwide, a cosmic event of unprecedented scale will unfold in our night sky. An asteroid the size of 3 massive football fields is going to pass closer to Earth than the very satellites we rely on for our daily communications. This will mark the closest approach of an object this large in recorded human history. Around 2 billion people across Europe, Africa, and Western Asia will be able to step outside, look up, and watch this massive space rock cross the stars with their bare eyes. Let's get the most important detail out of the way right up front. Apophis is not going to hit us. Scientists have run the calculations with extreme precision, and the collision has been completely ruled out for at least the next 100 years. So, this is not a doomsday story. But in many ways, the truth of what is about to happen is far stranger and more fascinating. The closer scientists look at this giant rock, the more the numbers stop adding up. And when it makes its close pass in 2029, Earth's intense gravitational pull is going to reach out and squeeze this body in a way nothing has in millions of years. By the time you finish watching, you will understand exactly why the people who study this thing are quietly on edge, and what they are about to find out about the fragile nature of our solar system. If you want to stay ahead of the biggest cosmic discoveries and ride along for this journey through the universe, make sure to hit that subscribe button right now. We are tracking the physics of this asteroid all the way to 2029. To really appreciate the scale of this flyby, we have to look at the orbital highway Apophis is traveling on. The asteroid is scheduled to pass approximately 31,600 kilometers above the Atlantic Ocean. To put that in perspective, the geostationary satellite ring, which carries our television signals, weather tracking data, and a massive share of global communications orbits at roughly 35,700 kilometers. Apophis is going to come in directly underneath them. It will pass at about 1/10 of the distance to the Moon, cutting through a region of space that is crowded with our own technology. An object this size, measuring somewhere between 340 and 375 meters across, has never been observed passing this close to Earth in human history. For a single night, a skyscraper-sized mountain of space rock will be visible as a moving point of light, brighter than the stars of the Big Dipper, easily trackable by eye without any telescope. But knowing the trajectory is not the same as knowing the object. While we have calculated the orbit of Apophis better than almost any other asteroid in our catalog, we still know very little about the rock itself. We know its address, but we do not know its character. For most of the time Apophis has been in our databases, that gap did not matter because the rock was floating silently in the void. But in 2029, everything changes. Our planet is going to grab hold of it, turning the flyby into a massive real-time physics experiment. To understand why this asteroid carries so much weight in the scientific community, we have to go back to when it first scared everyone. Apophis was discovered in June 2004, and within months, the preliminary calculations of its path sent shockwaves through NASA. The numbers showed a terrifying 2.7% probability of a direct impact with Earth in April 2029. While a 3% chance might seem low in daily life, for an object of this magnitude, it was alarming enough to set a record. On the Torino scale, which astronomers use to rate the threat of near-Earth objects, Apophis reached level 4, the highest level ever assigned to any asteroid before or since. For a short, tense window, this was officially the most dangerous rock we had ever found, and it already had a date attached to it. Fortunately, astronomers did their job. They kept tracking the asteroid, gathering radar data during its later passes in 2013 and 2021. By using powerful radar dishes at Goldstone and Greenbank, scientists managed to pin down its orbital path with extraordinary precision. The result was a clean all clear. An Earth impact was ruled out entirely for the next century, and the small probabilities of a strike in 2036 and 2068 dropped to zero. We now know exactly where Apophis will be in 2029, down to the kilometer. And that is where the real mystery begins. This historical context is crucial because it highlights the transition from a planetary threat to a scientific golden opportunity. When Apophis was first cataloged as a potential impactor, the global scientific community reacted with a mixture of urgency and dread. A rock of this size striking Earth would release energy equivalent to hundreds of megatons of TNT, enough to devastate entire regions, cause global climatic shifts, and claim millions of lives. The initial calculations of its orbit were based on limited telescope observations, which always carry a margin of uncertainty. In orbital mechanics, this uncertainty is represented as an error ellipse, a region of space where the asteroid is statistically likely to be. Over time, as more observations are logged, the ellipse shrinks. In the case of Apophis, that ellipse initially overlapped with Earth's physical position in space, which is what generated the initial panic. The threat was real enough to prompt governments and space agencies to start drafting plans for emergency deflection missions. It was the catalyst that accelerated the modern field of planetary defense, pushing researchers to think seriously about how to redirect an incoming threat. But when the radar data in 2021 finally collapsed that error ellipse to a narrow ribbon of space that completely misses Earth, the scientific community didn't simply pack up and move on. Instead, their focus shifted entirely toward a different kind of challenge. We realized that this close pass would bring a pristine, ancient space rock closer to our planetary laboratory than we could have ever planned. It is a free mission, a natural event where the universe brings the specimen directly to us. We do not have to spend billions of dollars and decades of travel time to reach a distant asteroid. Apophis is coming to our doorstep. This realization transformed the 2029 flyby from a potential disaster into the most anticipated astronomical event of our generation. Astronomers began to prepare global observation networks, coordinate ground-based telescope arrays, and design dedicated satellite missions to ensure that not a single second of this close pass goes unrecorded. It is the ultimate opportunity to study a near-Earth asteroid in unprecedented detail, and the findings will redefine our understanding of the solar system's history. The first real clue that the physical nature of Apophis is highly unusual came from a single stubborn measurement: its density. Density is one of the most revealing numbers you can measure about an asteroid because it tells you what the object is made of and how tightly its materials are packed together. A solid stony rock on Earth has a density of about 3 grams per cubic centimeter, but Apophis comes in at just 1.75. It is barely half as dense as the solid stone it is supposedly made of. There is only one logical way to explain this gap. The asteroid cannot be a single solid block of stone. It has to be full of empty space. The estimates put its porosity at around 40%. This means almost half of Apophis by volume is nothing at all. It is a rubble pile, a loose heap of gravel, boulders, sand, and dust held together not by solid rock, but by incredibly weak gravity. A rubble pile behaves more like a floating pile of dry sand than a solid brick. Its gravitational grip is so faint that a strong enough tug from an outside force could easily rearrange its entire structure. We have visited objects like this before and confirmed their existence. When Japan's Hayabusa spacecraft visited the small asteroid Itokawa, it found a classic rubble pile, a jumble of loose material with almost no solid core. More recently, when NASA's OSIRIS-REx mission touched the surface of the asteroid Bennu in 2020 to grab a sample, it found a structure so loosely packed that the spacecraft's arm sank into the surface like a pit of plastic balls. The surface behaved more like a fluid than a solid. Apophis matches these physical characteristics perfectly. It is a giant, fragile pile of cosmic debris hurtling through space. But the shape of Apophis makes it even stranger. When radar imaged the asteroid during its 2021 approach, it revealed that the shape was not a simple sphere or potato. It was highly elongated, pinched in the middle with 2 distinct lobes joined by a narrower neck. It looks like a giant peanut or a dumbbell. This shape has a name: a contact binary. It is formed when 2 separate asteroids drifted together long ago at very slow speeds, touched and stayed touching, held against each other by their own weak gravity. This is not rare. About 15% of near-Earth asteroids larger than 200 meters show this 2-lobed form. But common does not mean stable. A shape like this comes with a built-in weakness, and that weakness is the neck. The neck of Apophis is its seam, the narrowest and most fragile part of the entire structure. And a seam becomes highly vulnerable the moment an outside force starts pulling the 2 halves in different directions. To truly understand how a contact binary like Apophis forms, we have to look back billions of years into the history of the early solar system. In the chaotic environment of the early protoplanetary disk, dust and rocks collided constantly. While many of these collisions were violent, high-speed smash-ups that pulverized material, some occurred at incredibly slow speeds, mere crawling paces of centimeters per second. When two small asteroids drifted together in these gentle encounters, they didn't shatter. Instead, they touched and remained locked in a gravitational embrace. Over billions of years, these dual-lobed bodies survived, drifting through the asteroid belt and eventually migrating into orbits that cross Earth's path. However, this two-lobed geometry introduces a major structural vulnerability. The neck joining the two halves has a much smaller cross-sectional area than the main bodies of the lobes. This means that any mechanical stress, rotational force, or external gravitational pull is focused and concentrated at this narrow seam. If the neck fails, the two halves can split apart. In a solid asteroid, the material strength of the stone would easily resist these forces. But in a rubble pile, where there is no physical cohesion or chemical cement holding the rocks, together, the neck is held in place purely by the faint, shared gravity of the two lobes. The gravity at the neck is so weak that a human standing there could easily float off into space with a gentle jump. This fragile connection is what makes Apophis so susceptible to external forces, and it is why the 2029 closed pass is such a critical event. As Apophis comes within Earth's gravitational grasp, the differences in pull across the asteroid's elongated shape will put maximum tension on this exact seam, testing the structural limits of this ancient contact binary. The way Apophis moves through space points to the same conclusion. Most objects in space, if left alone long enough, settle into a simple, steady spin around a single axis, just like Earth rotates on its poles. But Apophis doesn't do that. Apophis tumbles. It rotates around more than one axis at the same time, causing it to wobble and roll as it travels through the void, never settling into a clean spin. The main rhythm of this tumble takes about 30.6 hours, and layered on top of that is a much slower wobble that takes around 263 hours. Picture a football thrown by someone who has no idea what they're doing, spinning end over end and sideways at the same time. That is how this asteroid moves. This tumble is not just a visual quirk, it is a direct fingerprint of what lies inside. The way a body rotates is set by how its mass is distributed. A smooth, uniform solid rock tumbles one way, while a lumpy, uneven body with denser regions in one place and emptier, looser pockets in another tumbles differently. The irregular spin of Apophis is telling us that its interior is not simple, which raises a critical question. What actually happens when you take a loosely held, lopsided pile of rubble and squeeze it with a planet? When we think about these cosmic forces shaping space rocks, it makes you wonder about our place in the universe. Why do you think so many objects in our solar system end up as loose rubble piles instead of solid rocks? Let me know your thoughts and theories in the comments below, and let's discuss how these fragile structures manage to survive the harsh environment of space. The force at the center of this story is one you already know: gravity. But more specifically, it is the same force that raises the ocean tides on Earth. Gravity gets weaker with distance. When Earth pulls on an object as large as Apophis, the near side of the asteroid gets pulled slightly harder than the far side. The entire body feels a physical stretch. On Earth, that stretch lifts the oceans. On a loosely bound rubble pile passing 31,000 kilometers overhead, it becomes something far more dramatic. Because Apophis is tumbling, different parts of its irregular body will swing into that line of maximum stress over and over during the hours of closest approach. Earth will not pull on Apophis just once. It will work the asteroid like hands kneading a lump of dough. This process of gravitational kneading is a fascinating phenomenon in celestial mechanics. Imagine a giant ball of pizza dough. If you pull it from one side, it stretches out. If you rotate it and pull again, it stretches in a different direction. Over time, the internal structure of the dough changes, becoming softer in some areas and denser in others. This is precisely what Earth's gravity will do to Apophis. Because the asteroid is not a solid block of granite, the gravitational pull will cause the individual boulders and pebbles inside the rubble pile to slide, roll, and settle into new positions. The friction between thousands of separate rocks rubbing against each other will generate heat, and the internal voids may open or close. Scientists call this tidal friction, and it is a major mechanism for energy dissipation in space. By measuring how much Apophis' spin changes during the flyby, researchers will be able to calculate the exact viscosity and mechanical strength of its interior, mapping the unseen pathways of its internal structures. It is a level of detail we have never been able to obtain for any asteroid, and it will give us our first true look inside a cosmic relic. Modeling groups that built virtual versions of Apophis out of thousands of simulated particles agree on the primary outcome. The asteroid's spin will change significantly. Apophis will remain a tumbler, but its spin rate could roughly double or be cut in half, and the direction its poles point will shift. The physical shape of the asteroid is also expected to flex, concentrating stress at the narrow neck. This could trigger surface landslides, shifting loose gravel and exposing fresh, unweathered stone that has been buried in the dark for eons. We could literally witness an asteroid partially resurface itself in a matter of hours, all observed in real time from our instruments on the ground and in space. There is a hard physical reason why Apophis will not simply fall apart: the Roche Limit. This is the boundary inside of which a body held together only by gravity will be torn apart by a planet's tidal forces. For Earth, and a body of Apophis's density, that limit sits around 18,000 kilometers from our planet's center. Apophis passes about 38,000 kilometers from the center, keeping it well outside the destruction zone. It enters the region where it gets stressed and reshaped, not the zone where it gets dismantled. This refutes the viral theories claiming that Earth's gravity will break Apophis in two, causing one of the pieces to slip through a gravitational keyhole and set up a future impact. The science simply does not support this. The detailed modeling predicts only centimeter-scale reversible flexing, not a break. And even if the neck did give way, the two lobes would drift apart at a speed of centimeters per second, moving only meters apart over hours, nowhere near enough to thread a keyhole less than a kilometer, wide that the combined body was already measured to miss. The impact remains completely ruled out. The online hype takes a real physical mechanism and blows it out of proportion, creating fear where there should only be excitement. To understand why the keyhole theory is so often misunderstood, we need to understand what a gravitational keyhole actually is. A keyhole is a tiny, narrow strip of space in the vicinity of Earth, usually only a few hundred meters wide. If an asteroid passes directly through this region, Earth's gravity will deflect its orbit by the exact amount needed to guarantee an impact on a future orbital return, perhaps 5, 10, or 20 years down the line. When Apophis was first tracked, scientists were worried about it passing through a keyhole in 2029, which would set up an impact in 2036. However, once the radar measurements in 2021 refined the orbit, we confirmed that Apophis will miss all known keyholes by a very wide and safe margin. The viral rumors online claim that because Apophis is a contact binary with a fragile neck, Earth's gravity will tear the two lobes apart, and one of these newly separated pieces will drift into a keyhole that the main asteroid was going to miss. But this scenario breaks down under the laws of physics. For the neck to break, the forces stretching the asteroid would need to exceed the gravitational binding energy holding the lobes together. Because Apophis stays far outside the Roche limit, the stretching force is simply too weak to overcome this gravity. But even if we assume the neck somehow failed due to a hidden structural defect, the two lobes would separate at an incredibly slow speed of a few centimeters per second. Over the hours of the flyby, they would drift apart by only a few meters. Since the keyhole is located thousands of kilometers away from the asteroid's predicted safe path, a drift of a few meters is completely negligible. The lobes would follow essentially the same trajectory as the original asteroid, missing the keyholes and passing Earth in complete safety. The science is definitive. Apophis is safe, and it will remain in one piece. For almost every close encounter in the history of our solar system, there was no technology in place to witness it. In 2029, that changes because we are sending hardware to meet Apophis. The first spacecraft is NASA's OSIRIS-APEX. This is the same spacecraft that successfully grabbed a sample from the asteroid Bennu and returned it to Earth in 2023. Time to reach Apophis right around its closest approach, it will pass about an hour behind the asteroid. Using Earth's gravity as a slingshot to catch up a week later, it will spend 18 months mapping the surface, reading its chemistry, and tracking its spin. Crucially, it will descend to within 5 meters of the surface and fire its thrusters downward, blasting away the top layer of dust to expose the fresh material underneath, letting us see inside a corner of this cosmic puzzle. It will not be alone. The European Space Agency, in collaboration with Japan, is building a second mission called Ramses. Designed to arrive at Apophis 2 months before the encounter, Ramses will measure the asteroid in its undisturbed state. This will provide the crucial before data, allowing us to compare it with the after measurements collected during and after the flyby. Between these two spacecraft, We will have a detailed before and after picture of an asteroid being reshaped by a planet's gravity. On that historic night, the public will join the science teams. While spacecraft orbit the rock, roughly 2 billion people will step outside and watch Apophis move across the sky. Behind the crowds, professional observatories will be locked on. Radar dishes will hit Apophis with radio waves to map its shape and spin in real time, while telescopes track its brightness for the subtle flickers that reveal surface changes. Almost nothing about that evening will go unrecorded. There is a practical reason why this study is so important: planetary defense. Somewhere out there is an asteroid that will not miss, on a year that has not been circled yet. If we ever have to push a dangerous asteroid off a collision course, we need to know what it is made of inside, because you cannot move a loose rubble pile the way you move a solid rock. We saw this in 2022, when NASA's DART mission crashed into the asteroid Dimorphos. The impact threw out a massive plume of debris, because Dimorphos was a soft rubble pile, pushing the asteroid harder than the impact alone would have. You cannot plan a deflection maneuver without knowing the interior, and the free lesson Apophis offers us in 2029 is the exact knowledge we will need to protect our planet in the future. Apophis is the most studied near-Earth asteroid in history. Its orbit is locked down, and it is not going to hit us. But it remains a sealed box, a loosely bound pile of rubble whose interior has never been measured. In 2029, our own planet is going to run the one experiment that can finally open it. The spin change, the neck flexing, and the landslides will all be recorded in detail, telling us what it truly is. If you want to stay updated on all the news, upcoming spacecraft launches, and new astronomical findings about Apophis, make sure to subscribe to the channel and turn on all notifications. The countdown to April 13th, 2029 has begun, and we want you with us every step of the way. To really put the importance of planetary defense into perspective, let's look at what would happen if we didn't have this physical data. In the past, scientists assumed that we could deflect any incoming asteroid simply by hitting it with a heavy kinetic impactor, essentially a fast-moving metallic spacecraft, to nudge its path. This approach works perfectly if the target is a solid, monolithic chunk of metal or dense granite. The impact energy transfers cleanly and the orbit shifts predictably. But if you hit a loose, porous rubble pile like Bennu, Dimorphos, or Apophis, with that same force, the results are entirely different. The asteroid acts as a giant sponge, absorbing the impact energy through the shifting of its internal boulders and empty spaces. Instead of moving as a single unit, the asteroid might simply swallow the spacecraft, or worse, shatter into thousands of smaller pieces that continue hurtling toward Earth along the same path. This is why the data we collect in 2029 is a critical baseline for our survival. By watching how Earth's gravity pulls on Apophis, and by observing how the OSIRIS-APEX spacecraft's thruster exhaust clears away the surface dust, we will gain a precise mathematical model of the cohesion and friction holding these rubble piles together. We will finally understand how much force is required to push a loose heap of cosmic gravel without causing it to fragment. Apophis is giving us a free, hands-on physics lesson that would otherwise cost billions of dollars to replicate. When the next dangerous asteroid is discovered on a collision course, the mathematical models we build during the 2029 flyby will be the exact blueprint we use to design the deflection mission that saves our planet. It is the ultimate test run, and the universe is delivering the subject directly to us. To truly understand the destructive potential of an object like Apophis, we only have to look back at our planet's recent history. In 1908, a space rock much smaller than Apophis, measuring only about 50 meters across, exploded over the remote forests of Tunguska, Siberia. The blast flattened over 80 million trees across an area of 2,000 square kilometers, releasing energy equivalent to 15 megatons of TNT. More recently, in 2013, a meteor only 20 meters wide entered the atmosphere undetected and exploded over the city of Chelyabinsk, Russia. The shock wave shattered glass in thousands of buildings, injuring over 1,500 people. Now, scale those events up to Apophis. Apophis is nearly 10 times larger than the Tunguska impactor and 18 times larger than the Chelyabinsk meteor. If Apophis were to strike Earth, it would not cause a global extinction like the asteroid that wiped out the dinosaurs, but it would completely obliterate a major metropolis, releasing energy equivalent to hundreds of megatons of TNT. The shock wave would flatten forests for thousands of miles, and the impact crater would span several kilometers. This massive threat profile is the reason why Apophis created such panic in 2004, and why it became the highest threat level ever rated on the Torino scale. Our ability to observe and analyze this giant peanut shape is thanks to planetary radar. When Apophis made its close passes to Earth in the past, astronomers didn't just look at it through optical telescopes, they hit it with powerful radio waves. Using the planetary radar systems at the Goldstone Observatory in California and the massive Arecibo Observatory in Puerto Rico before its collapse, scientists ran Delay-Doppler imaging experiments. This technique works by sending a radio signal toward the asteroid and measuring the exact time it takes for the echo to bounce back, along with the frequency shift caused by the asteroid's rotation. By combining these measurements, computers can construct a highly detailed three-dimensional model of the surface, revealing every ridge, boulder, and crater. This is how we first discovered that Apophis is a contact binary. Two separate boulders locked in a tight gravitational touch. The physics behind its chaotic tumble are equally complex. Most celestial bodies rotate around a single axis of inertia, but Apophis rotates on multiple axes, a state known as non-principal axis rotation. Over millions of years, internal friction within an asteroid usually dampens this wobble, slowly converting the rotational energy into heat and forcing the body into a stable single-axis spin. But for Apophis, the damping time scale is incredibly long, meaning it has kept its chaotic, wobbly spin since its last major collision in the asteroid belt eons ago. This wobble is incredibly valuable to physicists because it acts as an internal scale. The exact frequencies of the tumble depend on the moments of inertia, which are dictated by how the mass is distributed on the inside. By analyzing this wobble, supercomputers at planetary institutes can run simulations to predict the density profile of the interior, mapping out the voids and denser pockets hidden deep beneath the surface. This is where the upcoming spacecraft missions become absolute game changers. NASA's OSIRIS-APEX is equipped with an array of state-of-the-art scientific instruments, including a high-resolution camera suite, a laser altimeter, and thermal emission spectrometers. These tools will map the entire surface of Apophis down to the centimeter, creating a complete structural blueprint. When the spacecraft descends to fire its thrusters directly at the surface, the instruments will record the dust plume in high-speed video, measuring the speed and trajectory of the escaping particles to calculate the exact cohesion force of the surface material. At the same time, the European Space Agency's Ramses mission will use its own sensors to track the asteroid's thermal inertia and shape before the flyby, giving us the baseline data needed to measure the physical deformation caused by Earth's gravity. To process the mountains of data that will be collected in 2029, scientific groups are already running simulations on national supercomputers. These virtual models simulate Apophis as a collection of millions of individual gravitational particles, calculating the physical stress on every single boulder during the flyby. By comparing the real-world observations from OSIRIS-APEX and Ramses with these supercomputer models, scientists will finally solve the equation of asteroid interior physics. The resulting data will not only satisfy our scientific curiosity, but it will also serve as a literal shield for humanity. If we ever discover an asteroid on a true collision course, the knowledge gained from watching Earth squeeze Apophis will tell us exactly how to design a successful deflection mission, ensuring that we have the technology and physics models needed to protect our home planet from the next cosmic threat.